Okay, this is the circulating cooling water system. It's the system we just started up. The primary purpose is to condense turbine steam. It is pronounced turbine. I always call it turbine. I've done that for a lot of years, but it's incorrect. There are two types. You have the once through, which this is. We're pulling out of a reservoir up through the plant and back to the reservoir. This can be a lake or river. And you have the cooling tower. It comes out of the cooling tower basin through the surface condenser and back to the cooling tower. Your thermal energy is rejected to the air with cooling towers, and once your thermal energy is going back to the water, considered thermal pollution. Most new plants are cooling towers. Your main parts, you have your pump, discharge valve, and your surface condenser. The steam coming out of your low pressure turbine, it's under 28 inches mercury vacuum. There's about 100 degree steam coming in here. The key to this is the lower the vacuum, the more heat energy can be extracted in the turbine. Reason we dump it to a surface condenser instead of the atmosphere is it gives you a 30% increase in efficiency. And the water can be reclaimed. The water in these plants is very expensive as it has to be demineralized and cleaned up. Plus you're using about 6,000 gallons a minute of water. If the condenser vacuum starts climbing at 25.85 inches of mercury, you'll have 126 degrees, so you're not getting as much efficiency. And if the price of power is very high, like during the summer months, this could cost you thousands of dollars an hour just because you cannot get the vacuum. You can have high vacuum from drains getting left open somewhere that's coming back into the surface condenser, air leakage someplace, warm water, parts of the tubes getting airlocked. These plants are only 37% thermally efficient. That's a fairly good plant. As you can see, there's 1,460 BTUs a pound in the 2,500 psi steam coming into the turbine, and there's 1,105 BTUs in the 28-inch vacuum for the steam. So this energy here is being thrown away. It's the conversion from liquid to vapor, your entropy, that takes a tremendous amount of energy. Every pound of water you boil takes about 1,100 BTUs to convert from liquid to vapor. That's why these plants will use reheat steam. It goes to a high pressure turbine, returns to the boiler and heated to 1,005 from 600 degrees, so you get more heat energy, and it goes through the rest of the turbine. Also use feed water heating. This energy here can be reclaimed to reheat the feed water going back to the boiler. It's part of the steam goes through the turbine, is expanded, and heat energy is extracted. Then that can be used to heat the feed water, so it's more efficient. You keep those BTUs back in the system. So a lot of your heat energy is going out is waste heat. That's why these are not as efficient. Whereas a cogen combined cycle plant can be in the 60s. They're far more efficient in this style. So actually the vacuum at sea level is 29.92 inches at sea level of mercury. We use inches of mercury. You can use PSIA, pounds per square inch absolute. There's also metric. There's a bunch of different ways to measure the vacuum. The main point is you want as low a vacuum as you can get. It will increase your plant efficiency, but you don't want to get it too low. For the turbine manufacturers, you can drop out moisture in the backstage of the turbine, erode blading and erode tubes. It's hard to believe that the water and steam can be erosive, but it's like sandblasting this stuff. It's usually not a problem having too low of a vacuum, because maybe in the winter months you might see that. Summer months there's no chance of that happening. The next main part of this is the seal structure, called different names. It keeps a siphon effect on the system. That's its primary purpose. And you don't want too much of a siphon effect, or you start vaporizing water up here and you get air buildup, which will start causing condenser efficiency to drop to start airlocking the system. So you can see from the pump curve, at 120 foot head, these pumps won't pump any more water. That's the shut-off head. If the difference between the water level and up here, if you had a drain out up here and it was 90 feet, you can only pump 22,000 gallons a minute. If it's 60 feet from here to here, you can pump 98,000 gallons a minute. That's your maximum efficiency. So this basically creates a siphon effect and will take like 30 feet of the head off the system. So one pump will pump 98,000, and it would take 4 pumps to do this if you're dumping up here. So it really improves the plant efficiency. Some plants can actually change the height of this for various times of the year. Mostly it's just fixed. Okay, this is a circulating cooling water system, part 2 of the first part of this. This is going to be the individual components. This has a trash rack out front of the intake. This keeps out the large debris. You have rakes or some ways to clean this off. The next key part is your traveling screen. This prevents condenser tubes from being plugged up from debris. There's a chain runs on both sides with rollers. This is your screen section. The screen will be sitting like this, and here it comes up, down. To wash it, you run the screen, then you have a high pressure jet that blows the debris off the screen. This can be set up on DP or once a day run the screens. The maintenance on these, you have to lubricate these rollers every month. You need to inspect nozzles, make sure they're spraying the screens off well, not a lot of carryover debris. And if you get a high level here, this screen will actually jam into the frame and not move. At that point, you're going to have to take a pump off. You're going to eventually plug the screen off and start cavitating your pump. Screen wash water, usually a high pressure, 120 pounds or so. There's a motor and a gearbox on top, chain drive. You can see these rollers drop into this little slots on the wheels on upper and down the water, so it just moves. It makes a pretty solid screen across the face of this, keep out debris. The heart of this is the pump. This is actually a propeller type pump. It looks like a ship propeller down here in the bottom. There's a diffuser. As the propeller runs, it spins the water real fast. This takes the spin motion out of the water and helps develop some pressure. This particular pump uses rubber bushings. The reason they do that is the silt and debris in the silt and sand in the water does not do as much damage to the shaft. It kind of compensates for that. The key is you have to have your filtered water supply. You have to have lube water to these bushings. It flushes them and cools them. If it loses water supply in about 30 seconds, you can start damaging these bushings. Your water also lubricates your packing. This is a standard pump packing. Anytime you adjust these packings, you know a little bit of leakage is fine. Maybe go one flat on the nut when you adjust them. You got to be careful because the packing will heat up, and if you don't have much water flow, all of a sudden you'll seal off and start burning up the packing. So you got to be very, very careful adjusting these packings. They should leak a little bit. Another key part here is the discharge valve. There's no check valves in this system, and several of these type pumps do not have check valves. So the valve is closed when the pump starts, and in 10 seconds should be 20% open, then it takes 10 minutes to be full open. That prevents this system getting slammed with water when you start, and also limits the inrush current on the motor when it starts. When the pump shuts down, this closes and then the motor shuts off. If the motor trips, this shuts fairly quick because you're going to be dumping water back through the system. The motor is kind of a critical part. It's kind of a delicate part of this. It does have motor heaters. A lot of large motors do have motor heaters. They keep condensate from building up on the windings when the motor shut down. This motor, you have 3 starts per hour, 2 cold starts 15 minutes apart, and 1 hot start at 30 minutes. It is a 16-pole, 450 RPM motor. If you want to know how many poles the motor has, you take 7,200 and divide this number into that, and it'll give you the poles. Or if you have the poles, you can take the 7,200 and divide your poles into that, and it'll give you the RPM. It's kind of a handy equation. This thrust bearing is a critical part of this motor. It's supporting the motor weight, the pump weight, and the way the water being pumped. The pump's actually like a screw. All this weight of the water is actually pushing down on this pump. This particular thrust bearing will put out about 5 kW of heat. That's why it's water cooled. It's a Kingsbury style thrust bearing. With thrust bearings, you want to be kind of careful. When the motor shuts off, the oil's hot and the oil could actually get squeezed out between the shoes and the runner plate. And if the oil's still hot when you start, you're going to be bearing metal against the plate. Being a water cooled, I've never really seen a problem with these, but something keep in the back of your mind with thrust bearings. There's a lot of force on these, and when you shut down, you could have problems with the oil thinning out too much. Most of them are water cooled, so it's not an issue. There's also a thing called a sawdust addition tank. This is for real. You can use this if you have condenser tube leaks. I run fine sawdust. You don't plug your tubes, but it plugs up the holes. It works somewhat. They have different ways of putting stuff into seal tube leaks. You know, if you got 20, 30,000 tubes, you can get leaks in these things. You'll know you have a leak because your conductivity and your condensate goes up. You got drain valves, you got manways, you got vents. I can't overemphasize enough, when you start this thing up, make sure these are all closed, so you have a lot of water flooding the building. Another thing, to get rid of the air that builds up in here, as the water goes through, it's heated up, pressure, and the drop in pressure causes air to be released and water vapor. So slipstream is taken off to a drain tank, and then you got a liquid ring vacuum pump that pulls vacuum on this to help pull the air off. It has a rotor inside of it, and as the water moves, it creates a low pressure zone, pulls it in. Over here, a high pressure zone, and blows it to a vent tank. You get rid of the air, and the water comes back in. The difference in height here causes it to drain. Okay, show and tell part of this. This is a time over current relay. All large motors have time over currents. They also have high-speed differential relays. This is the same as most breakers using motor overloads. You have your time, which is based on the amount of current for the amount of time. Prevents the motor from overheating and damaging windings. Then you have instantaneous. This is a high current trip. As an operator, you can reset the time over current if you know the motor is just overloaded. Never reset the instantaneous. The motor needs to be measured. You have a fault in the system. Same as the smaller breakers. If the breaker trips, do not reset it. If it's a motor overload, you can reset that and run, as long as you are aware of what happened. The reason instantaneous you don't want to reset, this means there's a fault in the system. Something's gone to ground. Time over current just protects the motor from being overamped too long, being overdriven. What happens if you have an instantaneous, you've had a fault. This is an example of the cable actually going to the Circ Water pump motors. It's a 500 MCM, fairly large cable. And right here you can see where it faulted. It blew a hole through the side of it. There was a trip. So instantaneous current, it means something has gone wrong. You need to measure the motor, use a DC voltage and measure resistance to ground. It can tell you if you have wet windings or a fault or something has gone wrong with the motor. But you have the aluminum core, then you have a semiconducting material, then a shield. This is underground burial wire. It's good for 8,000 volts. It's 500 MCM. And it's capable of running a 2,000 horsepower motor. So, moral of the story, be careful when you reset breakers. There can be something like this, and you're slamming in the breaker and a tremendous amount of current, and it could blow the breaker up and do some damage to stuff. So for your own protection, never reset an instantaneous current trip. And overcurrent, time over current, verify why it tripped first before you go resetting it. And that's the end of that.